Hey guys, so in the last video we talked about how to get thrust from equations of fluid motion. So in this video I'll talk about how we can actually get lift from equations of fluid motion as well. So here is our control volume. So assume you have an airfoil. You can consider that the airfoil is actually in a wind tunnel test section, right? So, and you have these four walls marked by A, B, C, and D. Let the chord length of the airfoil be C, the length of the test section be L, okay? And then you have the velocity coming in from left to right, represented by this U infinity right here, okay? Now, all we have to, say for example, you don't have a way to measure lift using force transducer. So ideally, what we do is most tunnels have this like a sensor attached on the bottom of the wing so that you can actually get the lift force. Again, those of you who have not taken it to the flight, always remember that lift always acts perpendicular to the free stream. Doesn't matter the orientation of the airfoil, lift is always perpendicular to the free stream. Okay, so the way we get lift from most wind tunnels using a sensor, but um, we'll talk about in class that sometimes those sensors can actually get very expensive. We have sensors. The force sensor can range all the way from a few $100s to about a 1 million or $2 million. So there are different types and range of force sensors that are available, and not all force sensors operate the same way. So in the event that you don't have a force sensor, but but you need to generate or you need to determine lift. There is a way by which you can determine lift from using the pressures on the test section walls. And for that, we need to rely on equations of fluid motion to, for us to get an expression for lift. Okay. Now, moving forward, we will assume the flow is steady, the flow is inviscid, there's no body force acting, and there's no change in area, which means that the flow coming in is in the same going out. Okay, and some of these, as you know, may not be actually true in real life, but in order for us to get a reasonable explanation or simplify the equations, we can get away with assuming these four assumptions. But again, we'll briefly talk about in what cases where these assumptions will fail. Okay. Now, if we were doing this in class, I would ask you to do like a group discussion on how you can use the conservation of mass and momentum in this application to actually get the lift force, right? But, well, we're not in class and we're doing this online. So before you move on, I would like you to pause and think about how you can use the equations we talked about in the last video um, and apply this to this control volume to produce lift. Okay. All right. So hopefully you have done that. So moving forward, let's think about, thrust was actually the force in x-axis. So while applying conservation of mass and momentum, we always applied in the axis or in the direction of thrust, which is the x-axis, right? But in this case, the direction of lift is in the y-axis. So that means we have to apply the equations of fluid motion with respect to the y-axis, right? Because that's where the lift equation or the lift force is oriented. Okay, so when you apply conservation of mass in terms of like in x-axis, or in x-axis you will get rho 1 a1 v1 equals rho 2 a2 v2, but when you apply in y-axis, right? So we will assume that there is no velocity that's going through the face AD and BC. Okay, so there's no force, so there's no mass associated with in the y-axis. All the mass flux will is assumed to happen only in x-axis. So applying conservation of mass in y-axis, you'll get 0 equals 0. So that doesn't mean anything. So let's talk about conservation of momentum, right? So you may think that if there is no mass flow going through AD and BC, there may not be any momentum going through AD and BC as well. Well, that makes intuitive sense, but also one thing to keep in mind is that depending on your airfoil, or depending on what shape object it is, the airfoil actually curves the air around it, right? It curves it. So while the airfoil curves the air around it, there's a very slight component of velocity that is actually acting along y-axis. Okay, all right. So that actually has some momentum to it. You can argue that it also has some mass. Yes, you can even write conservation of mass in terms of y-axis, but you will get a very, 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 very small number, right? Because the velocity is very low. But when you multiply it with the mass with the velocity, the momentum you get, is also low, but it will allow us to derive an expression for us to generate lift. Okay, so let's look at the conservation of momentum in this area, right? When you do that, right, again, as I mentioned, that it is possible to have the momentum in y-axis. When that momentum interferes with the tunnel wall, right, the changes in momentum will actually manifest in terms of pressure variation because there is a change in velocity across the tunnel wall, right? Because as the flow, which curves around the object meets the tunnel wall, the velocity changes, and that changes in velocity translates as changes in pressure. So if there is changes in pressure, it goes for top and bottom surface. Using this expression, using this pressure, we can actually determine the lift force acting on the object. Okay, now let's discuss how that can be achieved. Now, using conservation of momentum, right, applied in y-axis. So rho Vy ds times Vy, this is the mass component, right? Then this is the velocity component. Mass times velocity will give you momentum. And here you have the pressure component as well, and the lift that is acting on the airplane, that on the airfoil, right? So on the left-hand side, right, let's break this into different constituents, right? So we apply rho Vy ds times Vy into A and B. There's no, we'll assume that there's no velocity component acting along, or the y velocity component acting along A and B. And CB, well, there's the y component. CD, let's assume again there's no y component, and let's assume there is a y component, a small y component that occurs due to the change in the way the flow goes around the object at the face AD and BC, right? So when we kind of divide these contributions to these different areas, what we can quickly decide is that there's no y component through A, B, and CD. That actually leaves with the y component in BC and DA, right? So the RHS, since there's no velocity, y velocity associated with A and B and D and C, we can assume that as 0. That only allows us to quantify the pressure variation along the surface of BC and CD. And yeah, so you get BC and then DA. So this should be BC and the upper, oh, this should be DA. Sorry, this should be DA right there. All right. So again, once again, the negative sign exists because the pressure is always acting inward, right? That's the pressure acting inward, right? But looking at the direction of the unit vector, right, the first term will remain negative and the second terms will the lift on the upper surface or the lower surface will become positive. Okay. So what this does is that moving forward, we can assume that rho y upper square, it basically, V goes inside and the A becomes the area of the test section on the length BC. And then the same goes for the lower surface. Say this is upper and then this is lower. It's the same analogy, the same expression for the lower surface. So rho Vy upper square times A minus rho Vy lower square times A equals the pressure difference, right? Now, here is where we make this assumption. Remember why I mentioned you can assume there's no mass going through the y-axis. Let's assume that, let's make that assumption here again. If there's no mass, then the momentum can also be negligible, right? So what we can assume is that the left-hand side is very, very low, that we can assume that it's almost equivalent to zero, or it's negligible, okay? So when we assume that the left-hand side is negligible because your Vy is really, really, really small, you can bring the left-hand side, lift to the left-hand side, which will actually give you this expression, okay? Lift is basically the pressure times pressure lower minus pressure upper times the surface area. Okay, what this means is that if you can quantify the pressure acting on the wind tunnel surface, on the top and bottom wind tunnel surface, for example, this is the pressure variation on the lower surface, and this is the pressure variation on the upper surface, you can find the difference in pressure, right? Integrate along the surface, and that will actually give you an expression for lift. Okay, now the reason why people do this is because sometimes your model is so big, right? Imagine a model of this size, right? And as the flow goes through the test section, it bends and then accelerates. But because of the test section walls, the flow cannot bend freely. In other words, it introduces what is called blockage, B-L-O-C-K-A-G, okay? And because of this blockage, the lift data that you actually get from force sensor will not be accurate, okay? That's why what people do is usually rely on the static pressure measurements, this PL and PU static pressure, on surface area so that they can actually determine the actual lift that the airfoil creates, okay? Um, Another way to actually ensure that the other way to actually use this setup is by ensuring that there is the static pressure variation across the upper and lower surface is constant. Okay. What I mean by that is if you put a large enough airfoil here with a high enough blockage, you can tailor the surface area of the tunnel in such a way that the static pressure remains the same. Okay, and some wind tunnels actually do that. Here is an example of a wind tunnel with pressure adaptive wall, which means that you see the cross section of the tunnel surface area, or tunnel surface on top. So using this adaptive wall mechanism, if they place a model something like this in here, say a car, right? Now, it poses a high enough blockage that the air going around it will, well, the walls will interfere with the air going around the car, which kind of poses, it interferes with the test measurements that's been taken. So what they do is they measure the pressure. I mean, I don't know if you guys can see, you have the pressure gauges on top, right? So they measure the pressure across the tunnel test section, and they deflect it in such a way that the pressure along a streamline remains constant. If they make sure to do that, then the tunnel will not introduce any blockage to the model which has been tested. Okay, otherwise, because of the test section and the air ramming through this small gap, that'll allow the flow to accelerate more, which interferes with the force testing. Okay, um, some tunnels, in order to prevent this, they design the test section in a way that it reduces the blockage. So here is an Aerodyne wind tunnel in North Carolina. Usually, is specifically designed to test, cars. Okay. Now, looking at the shape of the car, they designed the test section in a way that they can minimize the blockage. Okay. Again, keep in mind that we always have to make sure the static pressure across the walls are the same to avoid any blockage. But you can, if you have a square test section area, you can determine the static pressure measurements from the wall and actually determine lift. Okay, so that's pretty much what that's the significance of getting lift through equations of fluid motion. So hopefully this makes sense. Again, if you have any questions on this, feel free to let me know. Okay, but this is very important for you to understand, and not only the equations, but the practicality of that equation in in getting lift and also minimizing blockage in wind tunnels. Okay, all right. See you in the next video.